assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we want to determine what the induced EMF is in this square loop of wire here, a rectangular loop of wire. Given that the magnitude of the constant uniform magnetic field around it is 2.1 Tesla, and it is pointing with an angle 65 degrees above the surface normal of our rectangular loop here. So this angle right here. So the first thing we're going to look at is just what the induced EMF would be if our magnetic field went to 0 in 0.45 seconds. So if we recall, we can determine the induced EMF in our wire loop here with Faraday's law of magnetic induction, which states that the induced EMF will be equal to minus the change in the total magnetic flux through our loop divided by the change in time. So the change in magnetic flux can just be written as the final flux minus the initial flux, where since our magnetic field will be going to 0, we know that in the final configuration, our flux is going to be 0, since there's no field. And the initial magnetic flux we can determine by recalling that the magnetic flux for a uniform constant magnetic field is just going to be B times the area of our loop times the cosine of the angle between our magnetic field and the surface normal of our loop, which in this case, that angle is just going to be 65 degrees. Our area is just going to be the area of a rectangle, which is 0.55 meters times 0.35 meters. And the strength of our magnetic field initially is 2.1 Tesla. So I should put that. This is the initial B field there. So our induced EMF, we plug that in, it's going to be BIA times cosine of phi divided by delta t, where our minus signs canceled each other out here because we got one from the change in flux and one from Faraday's law of induction. Okay. So we're already solved for the thing we're interested in, which is the induced EMF. So all we have to do is just plug these numbers in. And if we do that, we'll get that the induced EMF is 0.38 volts. All right. So now we're going to do something similar for part 2. But instead of changing the magnetic field, we're going to change the area of our loop and try to produce the exact same EMF. So we want to figure out what that change in area per second needs to be in order to produce an EMF of 0.38 volts. So let's just refer back to our law of induction here. So we have minus the change in flux over the change in time. And now our change in flux is only going to be due to a change in area, right? So let's break that down a little bit so it makes more sense. The change in flux is equal to the final flux minus the initial flux, where the final flux is just going to be B times A times cosine of phi, where the magnetic field does not change now, the area does. So we'll just put area final. And then similarly, the initial flux looks almost identical except with an initial area. So we can factor out a b and a cosine of phi there. We'll have b cos phi times a final minus a initial. And a final minus a initial is just delta a. So this is equal to b times cosine of phi times delta a. So if we plug that in for our change in flux into our law of induction here, we'll have that the induced EMF is equal to minus b times the cosine of phi times delta a over delta t. So now we have our induction law in terms of delta a and delta t. So if we solve this for delta a over delta t, means we'll have to divide both sides of this equation by b cosine phi. We will have E, the induced EMF, over B times cosine of phi. And this is going to be negative. Okay. So we have the EMF we're trying to induce. It is 0.38 volts. We have the strength of the field being 2.1 volts, and we have phi being 65 degrees. So if we plug that all in, we'll get that the magnitude of the change in area over the change in time is going to be 0.43 meters squared per second. And since the sign over here was negative, we know that we will be decreasing our area in order to produce this EMF. So there you have it. We determined what the induced EMF would be in this loop here if we turned off the field from 2.1 Tesla to 0 Tesla in 0.45 seconds. And then we also figured out at what rate we'd have to change the area of our loop in order to induce the exact same EMF.